Hi guys, and in this video we're going to look at the Unit 4 Independent Task 4. So usual things, you should have had a go at the 5 questions and you should have got to a certain level of support. So just a quick reminder again, if you're not needing any level of support, that's really good. It means you just need to keep it taking over in the background, looking at it every now and again. If you get into level 1 or level 2 of support, then you need to make sure that you're doing a little extra work on this, recap it, do a couple of exam questions, and that's it. But if you get into level 3 or level 4, then that's a topic that you need to highlight now as one that needs a lot of work on it. Okay, so you need to make sure you're really going over things. Okay, going in detail, make sure you see a teacher and everything else. But apart from that, let's walk through each of the questions. So the first one, we have a uniform distribution. So we have a piece of string of length 20 centimeters is cut at a random point. The length of the longer piece is denoted by X, and the length of the shorter piece is denoted as Y. You may assume that X is uniformly distributed with an interval of 10 to 20. So X is uniform, 10, 20. Now what I'm going to do before I do anything else is I'm going to kind of draw my little graph going on. Okay. So X can be anything between 10 and 20. Let me change that to 10. And then my height should be 1 over b minus a, so 1 over 10 in this case. Okay, and I'm going to use that to my advantage now. So for part A, I want the probability that y is less than 8. Okay, so y is the shorter piece, so I want the shorter piece to be less than 8. Now, I haven't got a distribution for y, but I have got a distribution for x, so I need to make sure I change this into to work with my x's. Okay, now for y to be bigger than 8, x would have to be bigger than 12. Because if it was 8, we'd want it to be 12 because the total length needs to be 20. And as y gets smaller, the longer length has to get bigger. Now from there, we can use our just area of a rectangle. 1 over 10 is my height, times by, I want it greater than 12. So I want it 12 and above, so it's going to be 20, take away 12, which is only 8, which gives me 8 over 10 or 0.8. Either or will get you the mark. Okay. Part B, it wants express y in terms of x, well, y equals. Well, y is the shorter length, okay, and x is the longer length. Now, the total should be 20. So to get y, I simply do 20 take away x. Now, this part 2, there's 2 ways of going about it. Now, I'll show you the way that I think is easier. Okay, I want xy being greater than 64. Okay, now I've got something above to help me well. So I need to think of 2 numbers. If I times them together, it equals 64. And if I add them together, it gives me 20 because my total length should be 20. Okay, now doing this should give you the 2 values of 16 and 4. So x is my longer side, so it has to be 16, and y being 4, as is my shorter side. Okay, now from there, because I need a probability, I need to decide, do I want it to be, I want it in terms of x, so I'm going to use the 16. I've got to decide, do I want it bigger than x, or do I want it less than x? Okay, so obviously that equals 64, if I do xy. What I'm going to do here is I'm going to, okay, let's make it 1 bigger, which means y would have to be 3. If I did xy now, that gives me 51, which is less than 64. I want it bigger than 64. So let's check to make sure it works if I do the other way around. If I do 15, y would have to be 5. Xy would now come out as 75, which is bigger than 64. Which means, if I'm thinking about this now, I want the probability that x is less than, because this has got smaller, less than 16. I'm going to do the same thing again. So once I've got this set up bit by here, I can go from there and go, okay, that's 1/10. Like we did before, I want the area of the rectangle. I'm going to do 16, take away 10, because that's going to give me my base. It's going to give me 0.6. Now there's another way of doing it with substituting in what we got in part 1 in and making a quadratic, but I personally think that this one with a little bit of trial and error works a little bit easier. Okay, number 2, we've got a normal distribution question. Okay, and obviously you can see this is from one of the previous papers that have come up. Let's read all the information. Let's go from there. So we got Arwen collects data about household expenditure of food. He records a weekly expenditure for 80 randomly selected households across Wales. So we've got less than 40, 40 to 50, and so on, and then we've got the number of households for each one. Part A says explain why a normal distribution may be an appropriate model for the weekly expenditures. Okay, so trying to get me to describe why this is. Now, what you can't do is just say it's a bell-shaped curve, because it's not exactly a bell-shaped curve, is it? Okay, we can say, though, it's approximately symmetrical. We've got a peak in the middle, and then it tails off either end. So you've got two ways of describing it. Either I'm going to say, nice and straightforward, the data is approximately, you've got to have that word approximately, symmetrical. Okay, if you haven't got that word, it's not exactly symmetrical, so I can't say it is symmetrical, but it is approximately symmetrical. That's enough to say to get me the mark. You could have also said, as I was started before, it peaks in the middle and it tails off either end. So basically describing, okay, but again, it tends to, it's approximately, it's not exactly. That's what's going to be important for that part. Right, now, Owen uses a distribution of normal distribution of 64 and 15 squared to model the expenditure of food. Find the number of, so it's not asking me for a probability, it wants the number of households in a sample that this model would predict to have. So I am going to do the probability first. I'm going to do probability between 60 and 70. Okay, now, because it's in a normal distribution, I can just use my normal CD function. My minimum is going to be 60, my upper is going to be 70, and then I've got my two things from my distribution above. Gives me 0.2606. Now, that is the probability of it being between there. And if I look at how many there are in total, there's 80 in total. So if that's probability of 1, and I do it for 80, I'm going to simply times them together. Okay, which comes out, and if I round it, to 21. Okay, now if I look at the 60 to 70 mark, that was 18, so I'm a little bit off. Okay, so now let's do the same thing for part 2. Part 2, it wants probability that x is greater than or equal to 90. Okay, so 90 is going to be my lower limit. Okay, so if I look at the probability first, I'm 0.0415, and then I do the same thing again. If I want the number of, I'm going to times them together. So I'm going to times my 80 by my probability, gives me 3. Which again, if I compare it to the one above, is off where I want it to be. Okay, 21 is too high, and 3 is too low. Okay, so part C says, use your answer part B, comment on the suitability of this model. Okay, well, it's not very suitable, is it? Because 21 is bigger than it's supposed to be, and 6 is smaller than it's supposed to be. Okay, so I'm going to stick that. Okay, I'm going to say 18 is smaller than 21. It seems really basic, but it's important we do label things like this, okay? And 6 is bigger than 3. So it may not be a suitable model. May not be a suitable model. Now, part 2 wants me to explain how Aaron could improve a model by changing one of the parameters. So one of the parameters is either going to be changing the mean, or it's going to be changing the standard deviation. Now, in this case, what I want to do is my model's got a peak at 21, where I want the peak to be at 18-ish, okay? And I also want my other bits to come up a little bit and not tail off as quickly. Now, to do that, we would increase the standard deviation, okay? So that's what I'm going to say. They could increase the standard deviation. Okay, so that would flatten the curve out. Okay, it would make the peak not as high and the tails last a little bit longer. Okay. Now, part D is they now want to use the model. So Arwen's friend Colleen wishes to use the improved model, so whatever we've come up with now, to predict the household expenditure of food in Northern Ireland. Comment on this plan. Okay, it's not suitable. Okay, you could argue either way as long as you've got something sensible, but the not suitable is probably more likely for us to go for. Okay, as Northern Ireland capital, okay, may have different weekly expenditures on food. Okay, that's probably the one that we're more likely to go for. Again, you could have actually argued for it being suitable and say that Northern Ireland and Wales are similar in size, or could be similar demographic and all that kind of stuff. So you need to make sure that whatever you're saying has a really valid backup. So if you're not 100% sure if you'd get the mark there, please come and see me and we can talk about whether we think you've got a decent argument for that. Right, moments. Again, this is one that's come up in the past before, and it looks really, really complicated, okay? But we are just going to break it down a little bit more. In the diagram shows spotlights for us. So a spotlight system that consists of symmetrical track X, Y, that's suspended horizontally seen by two wires. So I've got wire 1 and wire 2. Now straight away, because there's wires, they must have tension in them. So let's call this one T1. Let's call this one T2. Each of the spotlights A, B, C may be moved horizontally along the corresponding shaded section in a track. So that's A, DA is DB is for B, and then DC is for C. So you can see the kind of lengths, the grey parts above them that they can slide along. The track may be modeled as a light. So notice there's a light uniform rod. Normally we have a mass to our rod, and we stick it in the middle, don't we? However, we can't do that this time because it's light, so there's no mass to it. Okay, so remember when you see that word, there's no mass, and the whole length of it, so this total length across, is 1.8 meters. Okay, now they've told me these two are 0.4, so this distance in the middle between wire 1 and wire 2 must be 1 meter. Okay, if I'm using just some nice easy maths down, I'm going to get rid of the 1.8 down here. Now, the wires are fixed at a distance of 0.4, which they told me from each end. Each spotlight can be modeled as a particle with a massive M. So each one of them is going to have mg coming down. Doesn't tell me what the mass is, but I can just say they're all mg. The distance the spotlights are shown. So I've got dA can go anything between 0 and 0.3. dB can go anything from 0.1 because it doesn't start against it. So it goes from 0.1 over to 0.9. And then same for the DC, it goes from 0 to 0.3. Given that T1 and T2 represent tensions, like I've labeled, show that T1 is given by this, and then find a similar thing for D2. Okay, so although this looks more complicated and more abstract than probably what you're used to seeing, okay, it's going to be important that we follow the same kind of steps. Okay, I've got moments here. Okay, I've got moments and I've got forces going on. So what I'm going to do is, if I want T1, I need to eliminate T2. So I'm going to take moments about wire 2. That's what I'm going to do for this first part. So for part A, I'm going to do moments about wire 2. Okay, that's going to eliminate the force on that. Okay, so I'm just going to go through each one and see if it goes clockwise or anti-clockwise. If I look, this C would go clockwise around 2. So would T1 would go clockwise, whereas the other two would go anti-clockwise. Okay, so on the left-hand side, I'm going to have my clockwise stuff, which would be mg times dc, because that's the length. I'd also have the tension one, which is 1 meter, because we said that's 1 meter, away from 2. Okay, then we have mg. If I look at B, I know that this distance is dB. Okay, so if I want the distance from 2, it's going to be 1 meters, take away dB. And then, very similar for the other one, dA is the distance from wire 1, so I want 1 meter plus dA for that one. And I'm going to rearrange this until it's T1 on its own, okay? So what I'm firstly going to do is I'm going to take everything over to one side. So T1, because that's just that times 1, is mg 1 minus dB plus mg 1 plus dA minus mg dc. Now they all got mg in common, so let's take that outside the brackets. Let's factorize that out. Gives me 1 minus dB plus 1 plus dA minus dc. Okay, and we can see that these two things here are going to cancel each other out. So I've got T1 is, those two are going to make 2. They're not going to cancel each other out. I'm going to get mg, 1 plus 1 is 2, plus dA is for that first, minus dB, minus dc, which is what they want me to get. Now what they also want me to do is find something for T2. Now I could now take moments about wire 1 if I wasn't sure about if I got this correct, but it wasn't show that, so I can use this. Okay, so what I'm going to do instead is I'm going to resolve vertically, which means I'm going to look at my forces going up and my forces going down. Okay, so going up, I've got T1 plus T2. Going down, I've got mg plus mg plus mg. Okay, so if I rearrange this, okay, I've got 3 mg here, and I'm going to take away T1, which is mg 2 plus dA minus dB minus dc. So my signs are going to flip here. I'm going to tidy things up a little bit. So I've got 3 mg. So mg is going to come out again. I've got 3 take away 2, which gives me 1. I'm going to have minus dA, because minus and a plus. I'm going to have plus dB, because of 2 minuses. And I'm going to have plus dc again, because of 2 minuses. And there's my answer for T2. Okay, so quite abstract, but I've followed the same method I would have done if I knew exactly what they were. Now for part B, find the maximum possible value for T1. Okay, so for the maximum value for T1, what I want to have, if we look at my diagram up here, what I want to have is I want to have every particle as far left as I possibly can. Okay, I don't want it necessarily close to T1. I want it as far left as it can. So all my moments are pushing over on T1, and my forces are pushing more on T1 than they are on T2. So I got to move everything to the left. So that means dA, I want it to be all the way to the left, so it's maximum, so 0.3. So I want dA to be 0.3. I want dB to be as close to wire 1, so I want it to be as small as possible, so that's 0.1. And I want DC, similar kind of thinking, I want that to be as far left as possible, so that'll be as small as it can, which is 0. If I use that and my equation for T1, okay, I end up with 2.2 mg. I still don't know what mass is, but 2.2 mg. Now for part 2, without carrying any further calculations, so I'm not expecting to do it again, write the maximum possible value for T2, give a reason for your answer. Now obviously I could go through the same process and work it out, but it tells me not to do any calculations. Okay, now it did tell me at the top that it's symmetrical track. Okay, if you look, DC and dA are the same, and dB lies perfectly 0.1 either side of wire 1 and wire 2. So this whole thing is symmetrical. Okay, which means the maximum value for T2 is going to be the same because it's symmetrical. Okay, so T2 would equal 2.2 mg because tracks are symmetrical. So question 4. force and friction. So get some diagrams drawn here. I've got an object of mass 45 kilograms lies on a rough plane inclined at alpha. So straight away, here comes my generic block on a slope. It's got a mass of 4g. It's got a weight of 45g. It would have a normal reaction going up, and this is alpha. They tell me tan alpha is 3 over 4. Okay, so again, if you what I recommend to do is straight away write what cos and sine of alpha would be. So sine would be 3 over 5, and this would be 4 over 5 using your triangles. A rope is attached, and it's how parallel of line the greatest slope of the plane. So there's my rope. So there's going to be tension in my rope. The coefficient of friction between the plane and the object is 0.5. So that's my mu. Go right over here. The object remains stationary on the plane. Find the least and greatest values for the tension. Now, there's two scenarios here. Okay, the first scenario is going to be that my rope is just stopping it from sliding down the plane, which means scenario 1 would be friction is also going up the plane. Okay, so I'm going to work out friction first. It's going to be constant anyway. So I've got my R should be 45g cos of alpha. Because remember, if that's alpha, that one there is alpha. Okay, that's resolving vertically, which would mean that that is 36g if I use my cos alpha from up here. Then I'm going to use my Fmax, is mu r. So it's 0.5 times 36g, which is 18g. And then I'm going to resolve parallel. Okay, so going up the slope, there's no acceleration, so going up the slope should be also going down. So going up the slope, I've got tension and I've got friction. Going down the slope, I've got my 45g sine of alpha. Now I know that this is 18g, so I've got t plus 18g is, and again I'm going to use my 3/5 over here, is going to give me 27g. Okay, so T would be 9g, which is 88.2 newtons. Okay, so that's the smallest it could have been. Now the other scenario, which I'll go over to the side here and draw again, okay, is the same picture. It's going to be the same amount of friction. That's my alpha. Tension is still going up the slope. R still going this way. Now the other scenario is that I've increased tension so much that I'm about to pull it up the slope, which means friction is now pulling me the other way. Okay, scenario 1 was me just holding it in place so it doesn't slide down, and now I've increased my tension so that it's just about to pull it up. And I'm going to do the same thing again. Now I already know what Fmax is, so I'm now going to resolve parallel again. Again, there's still no acceleration. I'm not actually moving. I'm just on the point of moving. Okay, it's remaining stationary, which means going up, which is tension. So you've got everything going down. So 45g sine alpha, and then the Fmax should also be going down now. Okay, so I've got 27g plus 18g, which is 45g, or 441 newtons. Okay, so the smallest it could have been is 88.2, and that's me stopping it sliding down, and the biggest it could have been is 441.1. Okay, and that would be me about to pull it up the slope. It's two slightly different scenarios you've got to consider there about what's happening. Okay, then last one, pulleys. Okay, it's pulleys and friction, this one. Diagram shows the body A lies on a rough plane. So again, it's rough. So let me just put some things going on here. The plane is inclined at alpha, where sine alpha is 5 over 13. Now, I only really need to know what cos alpha would be now, which would be 12 over 13 if I'm using my right angle triangles. body A is connected to a light and extensible string which passes over a smooth pulley, so I don't need to consider friction around a pulley, but it's light and extensible, which means the tension should be constant throughout. To another B which is hanging freely. The masses of A and B are 4 and 5 respectively. So A is 4G, B would be 5G. The system is in equilibrium with A on the point of moving up the plane. So A is about to move up, which means, because it was on rough, F max must be going down. And obviously R is always going to be my normal reaction, so perpendicular. Show that the coefficient of friction between A and the plane is 15 over 16. Okay, so the first thing I'm going to do is I'm going to look at this. When you've got pulleys, isolate your two things. So I'm going to look at either B or A first. I don't look at the whole system combined. I look at A and B separately. So I'm going to look at B first because I can find out what T is pretty quickly. Okay, so if I resolve vertically at B, okay, going up should also go down. So T must just be 5G. Okay, first bit, nice and easy for me to do. Okay, so I now know that T is 5G, which means it should also be the 5G at A as well. Okay, now the other thing I need to do is I need to work out what F max is before I go any further. Okay, so I need to know what R is before that, because F max would be mu R. So I'm trying to like work my steps here into my equations that I know. So let's do resolve perpendicular at A. Okay, so everything going up and down, in and out of the slope. So going out of the slope, I've got R. Going into the slope, I've got 4G cos of alpha. Okay, so R must be 48 over 13 G. I like to leave G in my answer because sometimes it can simplify out at the end. Okay, but if you have times by 9.8 all the way through, that shouldn't matter. Right, that allows me to rewrite my F max. F max is mu R, which would be 48 over 13 G and then mu. That's my final thing. Now, the only thing I've got left to do is resolve parallel. Okay, so I'm going to resolve parallel at A. Now, again, there's no acceleration, so I don't need to use Newton's second law. But I am just going to go straight into resolve parallel at A. Okay, so going up the slope, I've got tension. Going down the slope, I've got my 48G sine. That's part of the component of my weight going down. And I've also got the F max going down. Okay, and I can plug in everything I know. So T, we worked out to be 5G. I've got 48G sine, so 48 times sine, it's going to be 20 over 13G. And an F max I found to be 48 over 13G mu. Now, this is why I like to leave G in my answer, because look, they've all got G in them. So I can just get rid of them. Now, again, if you have times by 9.8, that's completely fine. It should work. Okay, and I'm going to rearrange this and solve it until I've got mu on its own. Okay, so if I take the 20 over 13 over, I get 45 over 13 is 48 over 13 mu. So therefore mu must be 15 over 16 as required. Okay, so that's it for this task, this task 4. If you've got any question, please just email me and ask. But apart from that, I will see you in the next set of tasks. Thank you, guys.